Welcome back, everyone. In this video we're going to explore the electromagnetic spectrum. We've already learned what electromagnetic waves are and how they're produced. And now we're going to look at this idea of a spectrum. The word spectrum comes from the Latin word spectare, which means to see. And I like to think about a spectrum as being a broad range that you can see, that you can visualize, and that you can process. So we're looking actually right now at the electromagnetic spectrum, and we're going to unpack this step by step and see exactly what we're looking at. You kind of get an idea that the wavelength is getting shorter as you go deeper and deeper into the electromagnetic spectrum. You see that the frequency is also getting higher, and there's an inverse relationship between frequency and wavelength. You can see there are different types of electromagnetic waves, and they've got different wavelengths of different orders of magnitude. You see buildings there, humans, butterflies. These are the different orders of magnitude of the different electromagnetic waves. And you can also see that visible light is a part of this spectrum as well, and we're going to unpack that as well. So in this video we're going to look at types of electromagnetic waves and their applications, wavelengths and frequencies of electromagnetic waves, and the visible light frequencies. So let's get started by taking a look at what the electromagnetic spectrum is. And what it is the full range of frequencies of electromagnetic waves. And we really want to start to unpack the wave speed equation. So recall, for wave speed, we had the equation v equals lambda f, right? Well, now we're going to replace this letter v with the letter c, because we've learned that lowercase c is the speed of light. So the speed of this particular wave, which is the speed of light, is equal to lambda f. Now, one thing we learned when we studied waves is that the speed of a wave is dependent only on the medium through which it travels. So if we're assuming that this wave is traveling through a constant medium, so let's say just empty space or even air, which is a pretty consistent medium, this c, this speed of light, is going to be pretty constant. Okay, so we're going to remind ourselves that the speed of light is going to be very constant as long as it's in the same medium. Which means that if you make an adjustment to either the wavelength or the frequency, so for example, let's say that you were to increase the wavelength of the wave, what would you expect to happen in the frequency? Well, if the speed of light is constant, then if you increase the wavelength, you're going to expect a decrease in the frequency. Likewise, if you were to decrease the wavelength, you'd expect an increase in the frequency. And that, of course, comes from the inverse relationship. We say that lambda, that's the wavelength, and f, that's the frequency, are inversely proportional. And you can very clearly see this relationship of inverse proportion if you solve, for example, for the frequency. If you solve the wave speed equation for frequency, you get the speed of light divided by lambda. And you can see that an increase in the lambda results in a decrease in the frequency, and vice versa. If you decrease that wavelength, you're going to increase the frequency. So that's a very important relationship, this inverse proportionality between wavelength and frequency. All right, so with this in mind, we're going to go ahead and we're going to draw a complete electromagnetic spectrum, okay? And in the space that we have here, what I suggest is that we draw two long lines across our paper. One like this, and one like this. Okay, and try to give yourself a good chunk of space in between these two lines. The top axis here is going to be the frequency, and that's going to be measured in hertz. And the bottom axis here is going to be the wavelength, and that's going to be measured in meters. And so we're going to start out this spectrum by looking at a very high frequency, and yet it's the lowest among the entire spectrum. We're going to look at 10 to the 8th hertz. Now the way we want to divide this up is as follows. Take your pencil, draw a halfway mark across the page, and then a very ending point across the page. So now what you have are, two sections, right? And then we're going to take these two sections and split those in half. So now we have 4 sections. Now we're going to take those 4 sections and split each one in half. And now we have 8 sections. And what we're going to do is very quickly label these sections. So we're going to start with this being 10 to the 8th hertz. This is going to be 10 to the 10th hertz. This is going to be 10 to the 12th, 10 to the 14th, 10 to the 16th, 10 to the 18th, 10 to the 20th, and 10 to the 22nd. All right, and then on the lower axis for wavelength, we're going to start out at about 10 to the second meters. So right around here, this is going to be 10 to the second, so about 100 meters. And then right around here is going to be 1 meter. And then right around here is going to be 10 to the negative second meter, so that's about a centimeter. And then right around here, we're going to have 10 to the negative fourth. And notice that these notches are just a little bit to the right of the notches that we have for frequency. So we're going to put a notch here, a notch here, a notch here, and a notch there. So 10 to the negative fourth, followed by 10 to the negative sixth, 10 to the negative eighth, 10 to the negative 10th, and 10 to the negative 12th. Okay? And this represents our full electromagnetic wave spectrum. So our first category of waves is going to show up between 10 to the 8th and 10 to the 10th hertz, a little bit after 1 meter. The dividing line is going to be right about here. And this first section are what we call radio waves. And we all know that radio waves are used for radio, but they're also used for telescopes. You might have heard of radio telescopes that pick up very, very deep background radiation from the universe. Radio telescopes are analyzing the radiation from stars, and they're how we get information from very, very deep objects in space. And the order of magnitude for the wavelength of radio waves is about equal to a football field. So in parentheses here, for the order of magnitude, we're going to say, okay, it's about equal to a football field. And of course, they get shorter, right? They get as short as 1 meter. But when you think about radio waves, they're generally pretty big. And that means something. That means that when you go through a tunnel, you might notice that you lose a radio signal in a tunnel. And that's because the wavelength is so long that they can't fit a full wavelength of that wave inside the tunnel. So you lose radio if you go through a very, very long tunnel. Okay, I want to show you an illustration of radio waves and how they're produced. So give me a moment to pull up a simulation. Here we go. In this simulation, you've got a generator, right? We start with a generator, and notice that it's got an AC voltage that's being applied to this circuit. And we learned from Faraday's law that if you run a current through a wire and you change that current, a changing electric field produces a magnetic field. So this red coil that you see here is going to be generating a magnetic field backwards and forwards, so up and then down, up and then down. And what that's going to do, it's going to generate a magnetic field through this upper coil up here, which in turn is going to generate its own electric field, because we know, once again, that a changing magnetic field produces an electric field. And so what that's going to do is going to push charges forward and backward through this blue wire. And so this represents here a charge that's being pushed forward and backward, up and down, over and over again. And what you see in this simulation are the electromagnetic waves spreading in all directions as a result of this, this moving charge. And what's kind of cool with this simulation, if I can pull it up, you can kind of change the direction here. Does it let me? Yeah, it lets me change the view. So check this out. I can look at it from a top perspective, look at it from the side. I think that's pretty cool. Very nice simulation here. And notice you can see once again the perpendicular electric and magnetic fields. It's kind of hard to see, but maybe you can see that. All right, good deal. Let's go back to our notes here. Oh, no, I have another simulation. I want to show you this simulation here. Okay, so this is from FET, from the University of Colorado. Now notice we've got a radio transmitter, and what's so special about this is that you can see how electromagnetic waves are generated by the motion of a charge. So you take an electron, right, and you oscillate it up and down. And by this electron oscillating up and down, you see that the electromagnetic wave is produced and it travels through space. Notice that as it gets further and further from the original source, it gets weaker as it goes. But over at this house, you see a receiver, right? So the radio station is a transmitter, and then the house represents a receiver. And what it does is it receives the wave, and the electron over here oscillates at the same frequency as the transmitter, right? So this antenna is picking up the oscillation, and it is oscillating in response to the electromagnetic wave. And I gotta tell you, while this may be a radio wave, the other electromagnetic waves like Wi-Fi and 4G operate in the same way. You've got an electron somewhere in space that's oscillating. Those cell phone towers that we are always looking for to get signal, you've got electrons oscillating from those cell phone towers. They're producing electromagnetic waves. Those are traveling through space, and your phone has a little receiver that picks up the oscillations of the electromagnetic waves and processes that as data, as bits, right? As what's it called? As binary code. And for Wi-Fi, it's really the same story. Whether it's Wi-Fi or 4G, you've got an electron that's oscillating up and down. This could be from a cell phone tower. And the receiver in your phone is going to pick up that oscillation. It's going to oscillate back and forth, and the frequency of that oscillation is going to be transmitted into binary code, which all computer software runs on. And that's how our phones and our computers get information from Wi-Fi or from 4G LTE cell phone towers. That's very cool. All right, let's back up. So we've explored radio waves. The next type of wave is going to go from this red line all the way to about 10 to the 12th hertz. So we're going to draw another line at about 10 to the 12th hertz, and this form of radiation is going to be called microwaves. Now you heard that I used the word radiation. Electromagnetic waves and electromagnetic radiation are the same thing. We're going to study waves as a form of radiation in the future, but for now, if I use the word radiation, it means the same thing as electromagnetic waves. All right, so microwaves, right? Applications here are obviously going to be your microwave ovens, but also you'd be surprised that the Wi-Fi frequencies and the 4G LTE frequencies are within the microwave range. Now they're not at the range. They're not going to, cook, human cells the way that the microwaves will. Although the World Health Organization does list cell phone radiation as a carcinogen if you keep it too close to your head. They've been known to cause brain cancer. So you don't want to, keep your phone next to your head all day long, right? You want to keep some separation there. But different frequencies of this microwave radiation can be used for different purposes. Some frequencies cook food, some of them are used for data, and you can see there's a very broad spectrum of frequencies here. And governments control these frequencies for different forms of communication. The phone companies are allowed to use certain frequencies, and the government and the military use their own frequencies, and those are always separate frequencies. So that's pretty cool. And like we said for the radio waves, the order of magnitude for the wavelength was a football field. For a microwave, think about a pencil eraser. Much smaller for the microwaves. All right, the next type of electromagnetic radiation is going to be infrared light. And that's going to go from microwaves all the way to a little bit beyond 10 to the negative 6th. So let me use a different color. I'm going to use black here. This is the infrared. And that's all one word, infrared. And the order of magnitude of the wavelength there is about equal to the tip of your pencil. So tip of pencil. And the applications for infrared is great for picking up heat. The heat that's given off by human bodies, for example, is within the infrared spectrum. So if you have night vision goggles, for instance, they're picking up infrared. They're picking up heat signatures from people or from animals, and that's what you see when you look at infrared cameras. All right, so beyond infrared, you're going to find the visible range of the spectrum. This is what we call here visible light. So as you can see, visible light is just another form of electromagnetic wave. After radio waves, after microwaves, after infrared, you then get visible light. But what's important to notice is that these are all the same thing. They all behave according to C equals lambda F. And notice that as the wavelength is getting smaller, the frequency is getting bigger. There's that inverse relationship we were talking about there. But visible light that our retinas can pick up is really just a small sliver of the electromagnetic spectrum. And we think we're special in the sense that we see visible light and we assume that's all there is. But animals can see many more frequencies of light than we can. They can see into the infrared, they can see into the UV. So let's take a moment and unpack the visible light a little bit. So often you're going to see this kind of drawn like this, with this kind of cone coming off of the visible light. And we're going to have a few different colors here. And if you give me a moment, I have some colors that I want to pull in. Thought I did. All right. Now, the colors that we're going to use here, of course, are the typical colors of the rainbow. We're going to start with red, okay? So I'm going to draw here our first color. This is red. Now, because red comes first, that means it has the largest of the wavelengths, and that means it has the lowest of the frequencies. Following red is going to be orange. Here's orange, followed by yellow. Oh, you can barely even see that. This is yellow. Oh, that's just comical. Nobody can see that. Let me write it in black. This is yellow. Okay. Following yellow, green. So here is the green. And you know what the next color is, blue. And then last color, violet. Alright, colors of the rainbow right there, right? Okay. Now, once again, red has the longest wavelength. It therefore has the lowest frequency. And violet therefore has the shortest wavelength and therefore the highest frequency. Okay? And a prism, like a raindrop, if you pass sunlight through a raindrop, under the right circumstances, you could get a rainbow, right? And you see all the colors kind of get spread apart, either through a prism or through a rainbow. We're going to study that in the future. Wonderful. So let's move ahead. Now, what would be beyond violet? Maybe ultraviolet, right? UV. So let's, in the next section here, call this ultraviolet. It goes all the way to just beyond 10 to the negative eighth meters, this is UV, ultraviolet. And ultra means beyond. It's greater than violet because it goes at a higher frequency than violet. And this is what's called UV. Now, the order of magnitude for the wavelength of UV is molecules. Now, why is that dangerous? This radiation, this electromagnetic wave, is at the wavelength of the size of molecules. That means that it can knock molecules out of place. So it's very damaging to our skin, for example, because it can take perfectly healthy cells and start knocking those molecules out of place, and that can be very damaging to our cells. So beyond ultraviolet, now we're getting into very, very high frequencies, very, very dangerous frequencies. We're going to take a look now at, let's use green. We're going into X-rays, and X-rays take you all the way to 10 to the 20 hertz. All right, these are X-rays. And X-rays are in the order of magnitude of atoms. And X-rays are even more dangerous than ultraviolet. X-rays can go right through human tissue and can actually damage human tissue, which is why when you get X-rays taken, you have to put on all that protective gear to protect your more vulnerable tissues. X-rays are very powerful, used for imaging, for medical purposes. And then finally, and I can see that I went a little bit too high there. Finally, the last category is gamma rays. So let's use red here. This is gamma rays. Beyond 10 to the 22nd, these are gamma rays. And a gamma ray might be produced by the collision of subatomic particles. When a particle meets an antiparticle, they annihilate each other and produce a gamma ray. And also nuclear reactions can produce gamma rays. So we're talking about particle collisions, and we're talking about nuclear reactions. And these are even smaller than atoms. They're on the order of magnitude of subatomic particles. And they can be used actually to split atoms. All right. Wow. So there you have it. This is the full electromagnetic wave spectrum. We covered radio waves, which are very long wavelength, as big as a football field, at a very low frequency. I mean, 10 to the 8th hertz is pretty high, but compared to the rest of the frequencies, it's very low. Followed by microwaves, followed by infrared, followed by visible light, followed by ultraviolet, followed by X-rays, followed by gamma rays, and that is the electromagnetic spectrum. Tune in to the next video, and good luck.